All right, it's now time to move on to section 2.4, which deals with continuity. We're going to first define what that is. So the definition. A function, f of x, is continuous at a point, we'll just call it A, if the following three conditions hold. So they have to all be true. There's going to be three things, and they have to all be true. Number one, f of A is defined. So this means I have to be able to plug in the number A. Okay, f of A is defined. Number two, the limit as x approaches A of f of x exists. We learned how to do that in sections 2.2 and 2.3. And then the third one is that the limit as x approaches A of f of x has to be equal to f of A. So number one says there has to be a point there. Step number two means that I have to be able to tell what happens as my graph gets close to A. And then number three means that those two things have to be the same. Okay, so basically what this means is as I get close to A, I have to get close to a point where f of A exists. Okay, so this is a fancy way of saying that you can draw the graph of f of x without picking up your pencil. Okay, there is a point there, and as I get close to that point, I'm getting close to where f of A is defined. Okay, so basically it's just a smooth line. Okay, a function is discontinuous. Sorry, I almost spelled it wrong. Let's try that again. Discontinuous at that same point A if any of the three conditions do not hold. So they have to all be true. So what I want to do first is I want to practice figuring out if a function is continuous at a point. So let's do some examples of being able to tell that. Example. Let's let f of x be equal to x squared minus 4 over x minus 2. And I want to know, is f of x continuous at x equals 2? Again, I want to check and make sure that all three of those rules do hold. Okay. So the first one is I need to know, is f of 2 defined? Which again means, can I plug in 2? Okay. So let's see what happens if I try that. F of 2 would be equal to 2 squared minus 4 over 2 minus 2. 2 squared is 4, so that's 4 minus 4 over 2 minus 2, which is 0 over 0, which is undefined because you cannot divide by 0. So since f of 2 is undefined, the answer is no, because my first rule already did not hold true, right? Because it had to have been defined, which it's not. So the answer is no. Easy enough for that one because it already did not hold for the first one, so there wasn't really a whole lot that I had to do there. Let's do another example. This time we're going to let f of x be piecewise, and there's going to be two parts. The first part says negative x squared plus 4 if x is less than or equal to 3. And then the second part is 4x minus 8 if x is greater than 3. And I want to know, is f of x continuous at x equals 3? So this time I'm going to use 3. So again, my first rule is I have to first see, is f of 3 defined? So I want to know, can I plug in 3? So let's try and see what happens. That should be a question. So for f of 3, since this is piecewise, I'm going to look and see which piece I want to use. Since this top part says x is less than or equal to 3, I'm going to use that one. So I know I'm going to use negative x squared plus 4. So that's going to be negative 3 squared plus 4. 3 squared is 9, so that's negative 9 plus 4, which gets you negative 5. So since I can plug in 3, I know that that's good. The first one does work. We're good with the first rule. So now let's move on to rule number 2, and I want to know, does the limit as x approach 3 of f of x exist? That's what I want to know now. Well, as we have seen, in order to do that, I've got to look at the left side and look at the right side and see if those are the same thing, right? So let's start with the left. The limit as x approaches 3 from the left. Since I'm going from the left, I'm going to use this top part because that's when x is less than 3, and so it's on the left side. So that's the same as saying the limit as x approaches 3 of negative x squared plus 4. That is a polynomial, and so we can just plug that in. So that's negative 3 squared plus 4, which as we saw on the first step is equal to negative 5. So now let's see what happens on the right side and see if those are the same. So as x approaches 3 from the right, that's going to be using the bottom part because that's when x is greater than 3. So that's the same as the limit as x approaches 3 of 4x minus 8. We can again plug in 3. 4 times 3 plus 8. 4 times 3 is, that's minus 8. My mistake. 4 times 3 is 12, so that's 12 minus 8. 12 minus 8 is 4. So on the left side, I get close to negative 5. On the right side, I get close to 4. So since those are not the same, we can say that the limit as x approaches 3 of f of x does not exist. Because as we have seen, those have to be the same, and they're not. And so since I break rule number 2, I can go ahead and stop and say that the answer is no. The limit does not exist, and so it is not a continuous function at x equals to 3. We have some more examples. This next one is also piecewise, except there are 3 parts and not just 2. Let f of x be equal to, again, it's going to be piecewise with 3 parts. 2x plus 1 if x is less than 1. 2 if x is equal to 1. And negative x plus 4 if x is greater than 1. Is f of x continuous at x equals 1? So again, let's check all 3 of those rules that I've got to pass. So the first rule, can I do f of a 1? So I'm going to look on here and see which part I want to use when I plug in a 1. So since I see right here, this is what I use if x is equal to 1, I'm going to do that one. And as I can see, the rule says it's equal to 2. So f of 1 is equal to 2, and that one is good because I can find a value. Next thing is I have to see if the limit as x approaches 1 exists. So again, we have to go from the left and then go from the right. So let's go from the left first. From the left, I'm going to use when x is less than the 1, and so that's going to be my top rule. So that's the limit as x approaches 1 of 2x plus 1. I can just plug in a 1 now, so that's 2 times 1 plus 1. 2 times 1 is 2, 2 plus 1, which is 3. So now let's see what happens from the right side. From the right side, I'm going to use the last rule because that's when x is greater than a 1, and so that's happening on the right side. So we're going to use negative x plus 4. Again, we can just plug it in, so that's going to be negative 1 plus 4. Negative 1 plus 4 is 3. So since from the left it's equal to 3 and from the right it's the same thing, the limit as x approaches 1 is equal to 3 because they are the same thing. So rule number 2 holds, and that's good. But now the third rule says that those two things have to be the same. What I got in step 1 and what I got in step 2 must be the same. Well, as I can see, f of 1 is equal to 2, but then in step 2 I get 3. So what this means is that the limit as x approaches 1 of f of x is not the same as f of 1. So since this third rule does not hold, again, the answer is no, because our third rule says those have to be the same, and they're not. We have one more example we're going to look at. This one's also going to be piecewise, but there's only 2 parts. Let's let f of x be equal to, again, piecewise with 2 parts. Sine of x over x if x is not equal to 0, and 1 if it is. And I want to know, is f of x continuous at x equal to 0? That's what I want to know. So again, first step, let's see if we can do f of 0. Well, I can see when x is equal to 0, it's equal to 1, so we're good there. Good with the first one. Number 2, we're going to do the limit as x approaches 0 of f of x. Normally with a piecewise, I'm going to do from the left and then from the right. But if I look right here, both of those are inside of one rule here, right? Because if I look at the number line, and 0 is right here, this top part is for everything except for this point. And so that takes care of the left and right. And so I don't have to do 2 parts here. I can just see that's the limit as x approaches 0 of sine of x over x. And as we saw in section 2.2, we did it at the very start, that is equal to 1. So we're good there. So now I just have to look at my third rule, which says those 2 things must be the same, and they are. As we can see, the limit as x approaches 0 of f of x, we said was equal to 1, which is the same thing as what we got when we plugged that in. So the third rule also holds. Therefore, we finally have one that is a yes, because it does meet all 3 of the rules there. So you may have noticed a pattern, especially whenever we did the rational function at the beginning. There is a pattern here, and it's going to help us out a lot. Here is the fact. I'll just write it down as a fact. Polynomials and rational functions are continuous at every point in their domain. So as long as I can plug in the value for x, then it will work out. Okay, let's look at some examples of that. Determine all the values of x for which the function f of x equals 3x to the 4th minus 4x squared is continuous. So as I wrote down on the fact right here, That just means every single point in the domain of this will work out. So I've got to see what is the domain. That's really what they want to know here, what the domain is. So remember, we learned how I find that is I want to see, are there any domain restrictions here? And there's not, right? The domain is everything. I can plug in whatever value for x I want to, and therefore it is continuous for all real numbers. Again, because there's not a value of x that I can't plug in. So they will all work out. Same question for this function. Let's do the same for the function f of x equals x plus 1 over x minus 5. We're going to do the same thing. So again, as I wrote down in my fact right here, as long as it's in the domain, we are good, right? So what they really want to know is what is in the domain. So just like we did over here, I want to see what the domain restrictions are here. Well, as I know, the denominator cannot be equal to 0. So if I add 5 on both sides, I see that x cannot be equal to 5. Therefore, we are good everywhere except for the 5. So that's going to be from negative infinity to 5, and then from 5 and everything else. So now that we know how to find where a function is not continuous, that's what we just did right here, we have to now learn what the different types of discontinuity are, because there are different types. Okay, there are actually 3 types. These are the types of discontinuities. The first one is if the limit as x approaches a of f of x exists, but f of x is discontinuous, that's a hard word, discontinuous at x equals a, we call it a removable discontinuity. So as long as the limit exists, then we call it removable. Okay. So the next type is if the one-sided limits exist, so the limit from as x approaches a from the left, and if the limit as x approaches the right of f of x, if those both exist but are not equal, then it's called a jump discontinuity. So if I can tell you what happens on the left and what happens on the right, but they're not the same thing, we call it a jump. And then the last one is if the limit as x approaches a from the left of f of x, or, I'll put and or because they could both, and or the limit as x approaches a from the right of f of x is positive or negative infinity, we call it an infinite discontinuity. So what I want to practice now is classifying what the discontinuities are. So what we're actually going to do is we are actually going to use the examples we already did. I'm glad I kept those whiteboards because we're going to use them. So we found 3 of the functions to be discontinuous. So we are going to classify what they are. So the first example we did was f of x equals x squared minus 4 over x minus 2. And we said we didn't like that one because I couldn't plug in the number 2, right? So what I want to see is which one of these three I'm going to be. So first things first, let's see if I can take the limit as x approaches 2. Okay, let's see if I can do that. Limit as x approaches 2 of x squared minus 4 over x minus 2. So as we have seen, my first thing I would want to try is to try just plugging that in, right? But I see if I tried that, the bottom would be 2 minus 2, which I can't do that, right? So I'm going to see if I can rewrite this in some way. I see I can factor the top part, which is x squared minus 4. I can factor that to be x minus 2, x plus 2 over x minus 2, which is helpful because then I can just cancel x minus 2's out. So that's going to be the limit as x approaches 2 of x plus 2. Now I can plug this in. I can just plug in a 2 and get 2 plus 2, which is 4. So since the limit as x approaches 2 exists, because I can get 4, this is a removable discontinuity. Removable discontinuity. I already forgot how to spell it. Discontinuity, there we go. You can tell I teach math because I can't spell. Anyway, and again, I know it is removable because the limit exists. Another example we did was this one. F of x is equal to the piecewise function negative x squared plus 4 if x is less than or equal to 3, and then 4x minus 8 if x is greater than 3. So the reason this one didn't work was because I could find the limit on the left and got the negative 5, and then I got the limit from the right and got 4. But since they weren't the same, we said that didn't work, right? Well, if I look at my discontinuity types, I can see type number 2 says the limit from the left is good and from the right is good, but that they are not the same. That's exactly what happened here, right? That's exactly the same thing. So because of that, I know this one was a jump discontinuity. I'm just going to say y'all know what I mean. And again, I know that because I can do it from the left and I can do it from the right, but they were not the same thing, so it is a jump. The third example we did was the piecewise function 2x plus 1, 2, and negative x plus 4. So what we saw here was it didn't work because they weren't the same, so I'm going to go through my types and see which one it is. And I would see it's the first type because I could actually find what the limit was as x approached a 1, right? I could get that. I got 3 there, and so that's good. So this would be removable because I could actually find what that is. So removable. Again, that's our first type because it did exist. Let's do an example of that third kind just so that you know what to look out for whenever you have it. So, example. Let's let f of x be equal to x plus 2 over x plus 1. What kind of discontinuity? I don't know why I'm having such a hard time with that word. Discontinuity occurs at x equals negative 1. I want to know what kind happens at x equals to negative 1. So in order for it to be the first type, I would have to do the limit as x approached negative 1. So let's see what happens whenever I do that. So that's the limit as x approaches negative 1 of x plus 2 over x plus 1. Normally I would just try to plug that in, but I see that I cannot. And so then I would try to rewrite this in some way so that I could get something good, right? But as I can see here, there's nothing I can really do here. There's nothing to factor out. There's nothing to cancel out. There's nothing I can do there to help me out. So how we have done this previously was we split it into two. That's the limit as x approaches -1 of just x plus 2. And then the limit as x approaches -1 of 1 over x plus 1. The reason we do that is because I can actually do this part right here. I could plug that in. -1 plus 2 is just 1. So this part, all of this just becomes 1. And so I can just worry about this part. Limit as x approaches -1 of 1 over x plus 1. We can see the bottom approaches 0. And as we had said, 1 over something very small is going to be really big. So this is equal to infinity. So because of that, if I look on my rules right here, that means it is an infinite discontinuity. Spelled it right on my first try. Look at me go. So that is how I tell which type I have. That's going to be a very helpful tool whenever we go to draw graphs. Okay, very helpful. We have another term we need to define. Definition. A function f of x is said to be continuous from the right at a point A if the limit as x approaches a from the right of f of x is equal to f of a. It is continuous from the left if the limit as x approaches a from the left of f of x is equal to f of a. So for these two, I really only care about what's happening on the right or the left. Now, you may want to know, why does that matter here? What is the point of that? Well, let me show you why that matters with an example. State the interval or intervals over which the function f of x equals the square root of 4 minus x squared is continuous. So remember, I can look at this by what numbers I can plug in, right? So let's see what I can plug in. Remember, we said that the stuff inside of a square root must be positive. And so let's see what makes that positive. That means 4 has to be greater than x squared. So I would take the square root of that, and I would see it must be between -2 and 2. That's the only way I can get something that's positive in here. So now I want to know, does it work at the -2, and does it work at 2? Well, notice that everything to the left of -2 is not defined, right? So I really only care about what's happening on the right, which is what I wrote down over here. So I have to find what the limit as x approaches -2 from the right is and see if that is good. Well, from the right, I can just work it out because that is defined, right? So I can just use the square root of 4 minus x squared. And if you plug that in, that is equal to 0. So I am good. So that's good. Do the same thing for 2 from the left side. Since everything is defined on that side, we can do the same thing, which is 0. So that's also good. So my point here is that because it is undefined everywhere to the left of this point or to the right of that point, I only need to worry about the right or the left of them. because everything else, it doesn't even count. So this would be interval from -2 to 2, including them. We have just a few more concepts we need to talk about in this section. This next part is extremely helpful and very nice, and it's going to be something we are going to use a variation of throughout this whole class, and that is this theorem. If f of x is continuous at L, and if the limit as x approaches a of g of x is equal to L, then what I can do is the limit as x approaches a of f composed with g of x is just f of the limit as x approaches a of g, which is just f of L. So the wording of this sounds kind of weird, but basically what this means is something we actually wrote down in section 2.3, I think it was, where if I have a limit outside of here, I can just bring it inside, which is going to save me a lot of work. We did that in section 2.3 whenever we had things like the limit as x approaches a thing, I'll just say a 1, of like the square root of x plus 2. I can bring the limit inside of the square root, and that's fine. To make it the square root of the limit as x approaches 1 of x plus 2. The same thing, okay? So let's look at an example where that might help us out. You know what? I think I can fit it right here, so I'm not going to waste a board on that. Let's find the limit as x approaches pi over 2 of cosine of x minus pi over 2. So what I can actually do is bring the limit inside of there and make that the cosine of the limit as x approaches pi over 2 of x minus pi over 2, which helps us out a lot because now I can just plug this into there. If I plugged in pi over 2 and made this pi over 2 minus pi over 2, that is 0. So we're doing the cosine of 0, which is equal to 1. So again, my point here is I can take the limit and bring it inside of there as long as it is continuous. So there's one more topic we need to cover in this section. And that is the Intermediate Value Theorem, which is extremely cool. Let's let f be continuous over a closed bounded interval, which we'll just call a to b, if z is any real number between f of a and f of b, then there exists a number c in the space between a and b such that f of c is equal to z. Now, I want you guys to pause this right here and write this down because this is a big deal. Okay, so let's talk about what this means, okay? So if I have a graph, I'm going to turn this over to the graph side. If I have a graph, and let's say A is going to be right here, I want to make it big. So let's say I have A right here and B right here, and my graph is continuous over this whole space, which means I can just draw it as one smooth line like this. Then let's say f, so that means, oh, I don't like the way I drew this, so I'm going to do it a different way. A and B, let's say f of A is up here. I'm even going to extend it beyond here. Like that. Sorry about that. So that means f of A is this point right here, and f of B is over here. And of course, I made them the same, so the illustration's not going to work good. There we go. Let's say, so f of B is right here. There we go. Anyway, what that means is if there is a value of y between f of A and f of B, so let's just say right here, this is what they mean as z. There's a value of y between them. So f of B is way down here, f of A is up here. So if there's a value of z between them, then there has to be a point between A and B where the graph lies at that point. So z occurs right here, and if we look at that, it happens between A and B. That's what that is trying to say. If there is a y between f of A and f of B, then the x corresponding to that must be between A and B. Now, it's okay to have some where it's not between them. Like I can see there's another one over here and another one over here. But that's fine. There has to be at least one between A and B there. So one more time, if the value of y is between f of A and f of B, let me draw it like this. So let's say f of A is here, f of B is right here, A is here and B is here. There has to be, so if there's a z between them, the corresponding x has to be between A and B. That's what this says. But the big point is that only works if it is continuous. That's the only time it works. Has to be continuous. So let's do some examples about when I can use this. Example, if f of x is continuous over the space between 0 to 2, and then if we have that f of 0 is positive and f of 2 is positive, can we conclude that f of x is always positive between x equals 0 and x equals 2 using the intermediate value theorem? So I want to know is, can I use this rule we just wrote down to say that it always must be positive? So let's see what this says up here. So this is saying f of 0 is positive, so it's somewhere up here, and f of 2 is also positive, it's somewhere up here. So let's think about if I can say it always must be positive. Well, if you think about that, all this theorem says is that if there's a z between them, then there must be a c but between A and B, right? It does not say what happens anywhere else. It does not say I can't go down here, because I can. I can do whatever I want to between there. It doesn't matter. It does not tell me anything else about what's happening between them. So the answer is no, because no information is given regarding what's happening between 0 and 2. Now, let's think about this another way. Let's say they changed the problem and changed it to say f of 0 is negative and f of 2 is positive. Then it asks, can we conclude that f of x has a 0 between x equals 0 and x equals 2? So what this wording is saying now, f of 0 is negative, f of 2 is positive, and I want to know, does it cross the x at some point between them? Remember, it says for any value of y between f of a and f of b, there is a point there, right? So 0 is between them, which means there has to be a value of x between 0 and 2 that makes this work. So in this case, we would say yes, that one does work because I have to pass through the x at some point to get from here to here. I have to pass it at some point. So the answer there would be a yes. But the way it was worded beforehand, I don't know what's happening between them, so there was nothing I could really do there. I have one more example. Let f of x be equal to 1 over x. So f of negative 1 is equal to negative 1, and f of 1 is equal to 1. Can we use the intermediate value theorem to conclude that f of x has a 0 between negative 1 and 1? So what this means is that on the graph right here, if I plug in negative 1, I get the negative 1, so that's this point, like right here. And then if I plug in positive 1, I get positive 1, which is this point right here. So they want to know, do I have to cross the x between them because of the intermediate value theorem? So I read what the theorem says and see, okay, is that something I can say? Notice what the very first line here says. Let f be continuous from a to b. Well, in this case, I'm trying to go from negative 1 to positive 1. And so is f of x continuous over this whole space? The answer is no, because I cannot plug 0 in for x, which is between them. So the answer is no, because f of x is not continuous over the space from negative 1 to 1. And I know that because f of 0 is between them, and it is undefined. So make sure you really read everything, and I can see here I cannot use this because f of x is not continuous at every point. Okay, so that is all I have for you for continuity, and that is it for chapter 2. I am very excited to get started on chapter 3, which is derivatives. So I'll see y'all with that stuff.